Hello everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we have finished the organic chem, but we have not finished the actual syllabus because there's two more topics. I know the last topic will actually not be covered in A levels this year, but I will still be doing that episode next week because for future people, I guess. Anyways, today's topic is electrochemistry, and it's the second last topic in the syllabus, I suppose. Yeah. And it's also a topic that you are very prone to making careless mistakes by getting confused over which is which and what is what, if you understand what I mean. Like for example, getting confused between a electrolytic cell and a electrochemical cell. So yeah, stuff like that. So anyways, I'll get into the learning outcomes and just hopefully finish it in a decent amount of time. Okay. So the first learning outcome is describe and explain redox processes in terms of electron transfer and or changes in oxidation number. Okay, so you know that the word redox is referring to reduction and oxidation. So when you're doing a reaction which involves both at the same time, because yeah, that's what's going on. So there's two different species reacting with each other, and one of them will reduce and the other one will oxidize. So the best way to balance the equation is to consider the number of electrons moving from one of the molecules to the other molecule in a sense. So for example, if one molecule, like if one species requires two electrons to go to the other form, like maybe it requires two electrons to reduce, and the other one will release three electrons when it oxidizes. Then when you balance it, you would have to make sure that the total electron transfer is the same for both of the species. So you would multiply and get 6 electrons. So you use the yeah the reduction, you times it by 3, and then the oxidation you times it by 2, and then you can get 6 electrons, and you can cancel all the electrons, and you don't have like random electrons popping up out of nowhere. Yeah, so I mean the electron won't just want to be alone, it will want to be a part of the molecule rather. And so this in terms of electron transfer. So in terms of electron transfer, the reduction requires you to accept electrons, and in terms of oxidation, you would be releasing electrons. So yeah, that's electron transfer. So the thing that's oxidizing transfers it to the thing that's reducing. If you look at the other way to look at it is the change in oxidation state. So at the overall change, we suppose it'll be 0. Like if you multiply it by the number of such atoms and stuff like that, you get 0. So let's say if like you know how to calculate oxidation number. For example, if you have organic compounds, you can kind of measure, like basically we have the atom in the center, the element in the center, and we have the other elements that are attached to this element. So if you look at each of them, see whether they're more or less electronegative to that as compared to the center atom. If they are more electronegative, you would assume that they have the electron density towards the outside. So the middle atom will actually have a positive oxidation state. But if it's the other way around, then it will have a negative oxidation state. But if you're not going to look at organic compounds per se, and we want to look at something like H2O, we know that O has like it comes like in its natural state. In order to bring it to the full octet, you have to add in 2 electrons, right? So to get O2 minus. So 2 minus is its oxidation state in H2O. But in hydrogen peroxide, there's two O's that form a -1 charge. Sorry, -2 charge together. So that means the oxidation state is -1. So you can use the ionic charges of state of your atoms. Yeah, so in terms of that, you can also calculate and then see which which like by how much is increasing and how much is decreasing. So let's say if like there's 3 carbon atoms in this particular molecule and it's the oxidation state of each carbon increases by 1 due to a reaction, then we know that the overall change is +3. And then if the other molecule will have to have an overall change of -3 to balance it out. Yeah, so you can use that to figure out the process as well. Anyway, so let's move on to the next learning outcome. So we are going to define 2 terms. The first one is the standard electrode or redox potential, and the second one is the standard cell potential. So the standard electrode potential is what you can see in your data booklet. There's this huge list of reactions, and it says you can either look at it in terms of alphabetic, or you can look at it in terms of the oxidizing power of that particular thing that's reducing. Yeah, so the standard electrode potential would be kind of like the for 1 mole of that particular, like, how do I say it? Well, if like it is expressed in volts, so that's the potential of a cell as compared to, sorry, that's the potential of that thing as sorry the potential of that equation as compared to the SHE. And so let's say if you put this with SHE, which is the standard hydrogen electrode, you will then get a like the difference in potential to in this particular reaction. So what's the difference between this and the standard cell potential? The cell potential is when you have 2 different setups and you can minus one from the other, so then you get the cell potential. So which one would you be minusing is, well, in this case, since we know that the standard electrode potential decreases with like the voltage is based on the movement of electrons, right? So as the oxidizing power decreases and the molecule becomes less reduced, then the potential becomes more and more negative. So what that means is that the equation would call for you to have the hydrogen one, sorry, not the hydrogen one, like the, how do I put this? You have the reducing one minus the oxidation one. So that's what you do. So for example, if you have the very first one in the list, which is the fluorine plus 2 electron becomes 2F minus, so that's the reduction one. And then if you minus the hydrogen, because hydrogen is lower in the list, and it will get oxidized by fluorine per se, if there was actually a reaction between fluorine and hydrogen for that matter, then you would be having 2.87 minus 0, which is plus 2.87. Of course, the 2.87 is already based on the standard hydrogen electrode, so yeah. So the next learning outcome is actually asking about the standard hydrogen electrode itself. So I'll just take a moment to describe that. Right, so if you look at the list again, the equation which actually has 0 potential is 2H plus, 2H plus 2E minus, which is electron, becomes hydrogen. So you have 2 hydrogen cations becoming a hydrogen gas molecule by accepting 2 electrons. So this particular thing, like the setup would be like a little container with some water, like some solution, sorry, not solution, just water, which has like hydrogen plus atoms only, like no other, and maybe there might be some OH minus ions, but the main thing there is the hydrogen plus cations. And the cations are becoming H2, and it's kind of like what happens when you try to break up water into, hydrogen and oxygen. Actually, no, that's not the one, but anyways. So I'll just draw it out for you and show you what it looks like. Anyways, so you have to draw it in that way, and you have to specify that the concentration of hydrogen plus is 1 mole per dm cube, and the pressure and everything is, because it's hydrogen gas, the gas collected should have a pressure of like the temperature of 298 K and 1 bar, pressure of 1 bar. So just use standard conditions for everything. So I'll draw it out to show you what it looks like. Because the gas will get to be in a particular container and it cannot just escape into the atmosphere or something, and that must have a pressure of 1 bar, and the solution must have a concentration of 1 mole per dm cube. So that should be in equilibrium to some extent. So that's the idea of the standard hydrogen electrode, and you can compare the other electrodes with the hydrogen electrode in order to get their electrode potential. And that's why the cell potential is based on 2 different electrodes, which means that you need both of them to create a cell. Right, so let's look at the methods used to measure the standard electrode potential of metals or non-metals in contact with their ions in aqueous solution, and the other one is ions of the same element in different oxidation states. Okay, so the first is metals or non-metals in contact with their ions in aqueous solution. So this is like, for example, your fluorine and fluorine minus, or if it's a metal, it's copper 2 plus, that kind of thing. And if we have standard electrode potential, we will use something like, we have to first look at the equation to figure out what we must use, because we have the anode and the cathode, right? But whatever stuff that you're using in the cell must involve everything that's in the reaction per se. So for example, if we were to look at the silver one, if you're looking at the silver one, we have silver plus and silver in the sense, and we can just compare. We can have a SHE on one side, and then we have the silver on the other side. So the silver one shows a silver plus electron minus becomes silver. So you need a silver electrode, and you need a solution that has silver cations, and the anion shouldn't react with the hydrogen for that matter. So that's what you need to do to figure out the standard electrode potential. So the next thing to know is which one is the cathode and the anode. Well, technically, if you know that this is gonna be positive per se, then you can tell that the since we have the reduction happening at the cathode and the oxidation happening at the anode in electrochemical cell, we can then figure out which is which and then put it accordingly. So since the silver is the silver is actually quite hard to do stuff with, because it's like, it's plus 0.80. So as compared to a hydrogen SHE, it is a reducting, like it'll undergo a reduction per se, and that means you would be putting the cathode of silver and you would be putting an anode of carbon or platinum, because if you don't need the metal per se, then you use carbon or platinum because they won't really react. So that's the general idea. So let's say if you have an iron electrode, then you use iron, but if you don't want it to react with the iron, then you use maybe a platinum or carbon. It depends on what exactly you're trying to do. if you're looking at a reaction that only involves Fe2 plus and Fe3 plus but no iron itself, no solid iron, then you don't use an iron cathode. So that's the idea of, you know, the equation. Use the equation to decide what you're gonna use. Yeah, so of course the connection of anode and cathode is, you know, anode is like the site where oxidation occurs, so all of the electrons are being taken in at the anode, and at the cathode all the electrons are being given out. So within a battery per se, like you can think of it like how in a magnet you would have the, you know, the, if outside you have the thing going out at the north, like the magnetic field and everything, but inside the magnet you have the field going from south pole to the north pole. It's different from the outside. So likewise in a battery, since the electrons want to go from, like the electron will want to go from negative to positive, and the battery in this case is the electrochemical cell. So the electrons will go from the anode to the, yeah, the anode to the cathode. So that's how it's gonna work. And the anode is the negative and the cathode is the positive. Yeah, so you can use that to figure out what is what. Okay, so the next, yeah, so you can use this for metal or non-metals. If you're using a non-metal, then you're likely to be using a carbon or a platinum electrode. And if you're looking at ions of the same element, you still have to do that as well. So the idea is that you need to know what will not react with the other thing. If let's say you need to put a salt of a particular metal to in order to get ions, you would want the anion to not be reacting in the equation. So maybe you use something like SO4 or nitrate anions, because they don't really react in the the electrochemical cell. Okay, so yeah, so in a way you can kind of understand how this works. So the next learning outcome is to calculate standard cell potential by combining two standard electrode potentials. So as I mentioned earlier, let's say you want to have a cell where one of the one of the electrodes is the, maybe, I don't know, Fe, yeah, Fe to Fe2 plus or something. And then the other one will probably be, of course, yeah, you have the Fe2 plus and Fe cell, and then the other one might be the maybe the water one, I don't know. Or maybe you can have the zinc one work. Maybe you could have the zinc one. So in this scenario, the two cells have different electrode potentials. So the zinc one has negative 0.76, and the Fe to Fe2 one has negative 0.44. So if you want to get a positive, yeah, if you want to get it to be positive, then what would you do? Yeah, you would have like negative 0.44 minus negative 0.76. So yeah, so what you would do is yeah, so if you have negative 0.44 minus negative 0.76, you would then get a positive number. And that means that the iron one will be the one that's reducing and the zinc one is the one that's going to be oxidizing. Yeah, so that means the iron will then become solid, and then the zinc will then become ions. That's what will happen. So basically just have the reducing one minus the oxidizing one. Right, so the next learning outcome is using standard cell potential to deduce the direction of electron flow and to predict the spontaneity of a reaction. Right. Mm. Okay, so if we want to look at the direction of electron flow from a simple cell, we know that I mentioned earlier about how the anode and the cathode thing works. So the anode will have like an excess of electrons that's pulling in because it is oxidizing the molecule by removing the electrons from there, and the yeah, so all of the negatively charged molecules will try to go towards the anode because the anode is the one collecting all the electrons, and the cathode will be the one that's providing the electrons, so that will end up giving, that will attract all the positively charged molecules or the molecules that want electrons per se. So we know that the electron flow is therefore from the anode to the cathode. And for that to happen, if you look at the battery in electrical circuit, yeah, actually you can kind of tell the electron flow already lah. So the electrons will flow from the anode through the to the cathode, and then it will go within the solution or whatever it is, it will go back to the anode. So that's how it kind of works. Yeah, so you can use the cell potential to figure out which is the anode and which one is the cathode by seeing which one is reducing, which one is oxidizing, and then you can tell which electrode is which. And in terms of the spontaneity of a reaction, we can find this, the standard cell potential, and then from there we can try to figure out the spontaneity by multiplying it by Faraday's constant and the moles involved in the equation. So that would actually be this equation called delta G equals to NFE. So yeah, so this is like, that delta G has to be negative to be spontaneous, but E has to be positive for it to be spontaneous. So if it's positive, then the reaction is spontaneous. If it's negative, it will not be spontaneous. So the cell potential has to be positive for that. And we'll look at the equation when the learning outcome comes, in a sense, because it's like 2 or 3 learning outcomes later. Anyways, yeah, so to predict the spontaneity, just look at whether it's positive or negative. Yeah. Okay, cool. So the next learning outcome is to understand the limitations in the use of standard cell potentials to predict the spontaneity of a reaction. Okay, so as we know from a previous time, we know that some reactions may technically be spontaneous, but they don't actually happen in great detail or something. Like, for example, it's not like the diamond will suddenly become graphite in 1 second or something, because the spontaneity is just one thing. Like, that the thing that we use to determine spontaneity is just one of the many factors, and there could be other factors that affect whether the reaction actually happens or not. And yeah, that's pretty much it. Okay, so the next learning outcome is to construct redox equations using the relevant half equations. Okay, so we have all these half equations over here in that list, and you can then use it to construct redox reaction equations. So as I mentioned earlier, you have to balance the number of electrons, so that's the main thing you need to do here. So you can write down the reduction equation, write down the oxidation equation, and then you multiply them accordingly to balance out the electrons. And once you're done, you have to see what kind of solution it is. If it's acidic, then you account for the hydrogen plus, or if it's alkaline, you account by adding OH minus. So what I mean is, when you multiply the equation, sometimes you will have a charge. Like, not really the electron themselves, but the atoms will have a bit of a charge disparity. And to deal with that, you can add in some you can add in some H plus to balance things out. But if it's an alkaline solution, then you won't really be having random H pluses popping up here and there. So you rebalance it by adding OH minus to everything, and then you get H2O on the other side. So that's the idea of this, because there's always water involved in it, so you can easily do this method of using H plus and OH minus. So let's say we apply this to our equations here. Let's use the KMnO4 kind of thing. So manganese MnO4 minus plus AH plus 5E minus becomes Mn2 plus OH2 4H2O. So when you try to balance this with something else, like maybe the K, actually potassium one is too simple, it's just K plus an electron. So when you balance it with that, what you do is you would put the like, because the manganese one is very positive and the potassium one is very negative. So you would put the manganese one as the reduction one and the potassium one as the oxidation one. So you flip it accordingly, and then you multiply the potassium one by 5 because there's 5 electrons in the manganese one, and from there you can then plus them, and then you can see whether there's a balance of water. In a sense here there is, because the manganese one is preserved as it is. And in terms of the charges, we have, so there's a charge balance and you don't have to worry about it. In the end, the example I chose doesn't really have anything to balance. Anyways, so that's how you construct redox equations. So state and apply the relationship. So this is the thing I'm talking about. So delta G is equals to the negative of moles times Faraday's constant times E. So times E, which is the potential. So what does this mean? We have the E because it's in volts, so we had to convert that into delta G, which is an energy thing. And in order to do that, we would first multiply it by the mole of species, the thing that's reacting, and after that you would need to multiply it by Faraday's constant, which is 9.65 times 10 to the power 4 Coulomb per mole. That's why we need the mole. So when you times Coulomb and volts, you will then get your energy. That's pretty much it. And the reason why it's negative is because when there's potential being produced, it means that the reaction is spontaneous. So in theory, the energy is being released, so delta G is negative in a sense. Anyways, so the next learning outcome is to predict qualitatively how the value of an electrode potential varies with the concentration of the aqueous ion. So we always have to be worried about making, like, when you draw your cells and everything, you have to make sure it's 1 mole per dm cube and 298K and 1 bar. So why is it particularly 1 mole per se? If we have this very familiar example, which is something to do with the chlorine, something to do with chlorine. So we can see the one for chlorine, which is positive 1.36, and if we look at the one for water, where is it? Wait, I'm searching for the water one. I believe it's the 1.23. So in normal, in standard conditions, we can see that the chlorine one is more positive than the water one, and therefore the chlorine is the one that, so if we are comparing this with the one for hydrogen, where's the hydrogen? Sorry, hydrogen is one of the equations. The water becoming hydrogen is one of the equations. And we already have that the 2H2O plus 2E becomes H2 plus 2OH. So usually if you to just simply electrolyze water and there's nothing else in the water, you will just get hydrogen and oxygen, because yeah, that's what happens. But if you had some chlorine atoms in the solution and it were 1 mole per dm cube, well, in theory, the in order to get the oxygen, you would want the the O2 to be less positive than the chlorine. So yeah, that the O2 will still be produced in very dilute solutions of NaCl. So yeah, the scenario would probably be using NaCl. But if you have a very concentrated brine where the chlorine is so high that the value of the chlorine electrode becomes lesser than 1.23, because it is no longer the standard one, so it's no longer the one with the circle but just simply E. So it will actually become less positive than 1.23, and then chlorine gas will be produced until the concentration drops to 1.1 mole, or like comparable to the water itself. Yeah, so that is why we need that's why the concentration actually affects the electrode potential. So if you really want to know how it truly affects it, for the chlorine one itself, let me give an explanation. So the chlorine one shows Cl2 plus 2E minus becomes 2Cl minus, and we know that the potential decreases as the thing becomes less oxidizing, as the reduction decreases. So as you can see here, we want the opposite to happen. We want oxidation to happen. So in order for it to happen, we need the potential to decrease. Yeah, so when you increase the amount of Cl minus, it will be more likely to oxidize into Cl because of the Le Chatelier's principle, and it will want to move the position of equilibrium to the left. And therefore, the potential will also decrease because it's more likely to, you know, oxidize rather than reduce. Right, so what's the next one? So annoying to scroll up and down. Okay, so the next one is right. Okay, state the possible advantages of developing other types of cells. Oh, okay, so this is just a quick aside to real life examples. We have the hydrogen oxygen fuel cell, which is basically using water to using the idea of water electrolysis. And this can be used to as like a little battery, and that is actually pretty cool, right? So yeah, so you can use the hydrogen oxygen cell in order to do some stuff, I guess. And people are thinking, okay, let's use it in electric vehicles and stuff like that, because it requires, it's like a bit more eco-friendly than something that produces CO2 and all that. But the problem is it's a bit, and it may not really be the best cell on market, I suppose, but it is still pretty good in a sense. So yeah, so in that sense, if you have the hydrogen oxygen fuel cell, it's a bit more eco-friendly, and it's pretty simple. Just get some just water related kind of stuff going on here, and it doesn't produce any CO2 or anything else. But if you look at batteries per se, if we have better batteries, this is actually more worthwhile for electric vehicles. So battery storage is actually an important research area. So if you get batteries that can store a lot of energy and then put it in a vehicle or something, it's much easier to run the vehicle sometimes if you were able to do that. But the problem is right now all the batteries are quite big and bulky. But if we manage to get smaller and much more efficient batteries, we can power a lot of things without using fuel per se. And it might give a nice consistent voltage and stuff like that, because it's a battery and it's kind of self-contained in a way. And if you manage to do a really good battery, you can even have like lower mass and a bit more efficient for what it's worth in the sense. And that's why right now we have like, batteries in our iPhones and everything, the lithium ion batteries, and I think that's like they're already quite important. If they're rechargeable, it's even better, that kind of thing. So I think they'll get more prominence in the future. Anyway, so the next learning outcome is about the Faraday and the Avogadro constant here. So we know that the Faraday's constant is Coulomb per mole. So the Coulomb comes from the charge of the electron. So we have the charge of the electron, and the mole comes from mole. So what does it mean to have 9.65 coulombs per mole? It just means that 1 mole of electrons has this much charge. That's pretty much what the Faraday's constant is. So actually the n in the delta G equals to negative n Fe is equivalent to the moles of electrons being transferred. So that's what you're actually looking for here. So you're actually looking at the moles of electrons being transferred, and then you times it by Faraday's constant and to get the overall charge per se, and then you times that by the voltage, because the voltage is basically so it's basically the current times resistance. Usually that's what we learn in physics, and current is charge over time. So if we times the charge by voltage, you get the energy actually. So there's a way to prove why this is equal to energy. Yeah, you can figure that out yourself. It's just some unit crunching and you get the answer. So anyway, so the point here is that Faraday's constant is equals to Avogadro's constant times the charge of an electron, and therefore you don't actually need the value of it here. You just need to times 1.6 times 6.23 times 10 to the power of 23, and then you get the answer. Yeah. Oh, sorry, 1.6 times 10 to the power of negative 19, not just 1.6. That's why you get 9.65 times 10 to the power of 4. I hope it adds up. Yeah, it should work. So the next learning outcome is to predict the identity of the substance liberated during electrolysis from the state of electrolyte, position in the redox series, and concentration. Okay, so now you're moving on to electrolysis, and electrolysis is the other way around. So you supply some electricity to push the reactions in the opposite direction. So it's basically just the opposite of an electrochemical cell plus some extra energy source to get things going. And basically you're trying to do a non-spontaneous reaction instead. So that's the idea of electrolysis. And so in electrolysis we are basically passing some electricity to get something done that we otherwise wouldn't get done. And right, so if we have something like silver, and you want to purify the silver, basically you have this electrolysis to purify it, and then you put like 2 carbon electrodes on both sides. So what happens, sorry, not necessarily carbon electrodes on both sides. Basically one side will be the impure silver, the other side will be, maybe if you want, you have a pure sorry, not silver, I think copper would be good. So impure copper, and on the other side you have a pure copper rod. So the impure copper will then electrolyze. It'll undergo this reaction and then it'll oxidize into copper 2 plus, and then the solution is copper 2 plus solution. So the electrodes when the copper 2 plus on the other side will then reduce back into copper, and you'll get a pure copper on the other side. So in terms of the impurities, the silver won't do anything, so it will just happily go and settle at the bottom. It doesn't even get oxidized, because silver is, like if you look at the value of silver versus the one for copper, we know that silver is plus 0.8, right, and copper is plus 0.34. And since silver has more positive redox potential, that means it's more likely to actually not even oxidize. It's a more of a reducing thing rather than an oxidizing thing, and therefore it won't even bother to oxidize into the solution and just sit at the bottom of the tank or something. As for the zinc, because copper will also have zinc in it, so zinc, as we saw earlier, is negative 0.76, so it's extremely negative and would very, very readily oxidize because it's kind of negative. Actually, no, it's not the most extremely negative thing, but it's still pretty negative compared to the copper. And therefore, the zinc will just oxidize into the solution as well. But when you go to the other side, the zinc will not get onto the copper, the pure copper, because it is more negative than the copper itself. So it doesn't like to reduce back into zinc when copper is also there. Copper will be preferentially reduced. So you might be wondering which side is which, like which electrode is which. So in the electrochemical cell, you have the anode being the oxidation area and the cathode being the reduction area. But in the when you have a electrolytic, if you have an electrolytic cell, in the sense, you would be doing it the other way around. And so the cathode will have the oxidation and the anode will have the reduction. Which I think might be easier to remember just because like oxidation involves becoming more positive and reduction involves becoming more negative, and cathode is positive, anode is negative. Yeah, so just think of it that way. And so yeah, so since the cathode is now having the oxidation, at the cathode is where the copper will, like impure copper will be, so that's the cathode, and the anode will be where the pure copper will be, because you want all of the copper ions reduced back into copper. Yeah, so you can just use this to explain what exactly happens. So in this case, we have a solution of copper plus 2 plus. If the solution doesn't really have a lot of copper 2 plus, it might be hard to actually get copper back onto the thing. Or the solution has metals that are, not exactly zinc or silver per se. Actually, in a sense, all of the other metals that are not copper will either just, become like do stuff like silver or do stuff like zinc. So in a way, you don't have to worry about it. But yeah, okay. But it also depends on how much of that metal is there. Like if there's too much zinc, then you have to really wait for all of the zinc to oxidize first before the copper oxidizes. But since there's usually a smaller amount of zinc, even if the zinc is preferentially oxidized into the solution, there'll still be enough copper, like the copper will still get oxidized and then rejoin onto the pure copper. Anyways, where was I? Okay, so in terms of the other factors, which include the solution, the state of the electrolyte, if we have a molten electrolyte, which is like, you use your aluminium and you want to melt the aluminium into your solution, then you would actually still get aluminium 3 plus because it is now molten. Which is different from using a solution, because the solution would involve certain anions and sometimes the anions will react. But if you have only molten aluminium, then you can do stuff with just the molten aluminium, and that would be pretty cool, but also requires a lot of energy because you need to actually melt all of the aluminium. Yeah, so if the electrolyte is molten, then yeah, it doesn't really have a solution per se, but rather its state itself is in a molten state. Right, so yeah, so basically it can only be a mobile charge carrier if it's molten or if it's in the aqueous state, so that's why it needs to be in one of those states for the electrolysis to go on. And yeah, the position and the redox series is what I was talking about. So you can actually use these electrode potentials to figure it out if you cannot remember the redox series. And the concentration, as I mentioned earlier, which is the one with the chlorine concentration. So you had to, so when you're doing electrolysis with chlorine, then it will actually matter. The decreased concentration of chlorine will increased concentration of chlorine will make it more likely to become chlorine gas, and a decreased concentration will make it more likely to remain as a chlorine minus. Oh no, that's not the last one. There's two more. Okay, so the next one is to calculate the quantity of charge passed during electrolysis. Okay, so just think of electrolysis like the opposite of the electrochemical reaction, so it's just the opposite in the opposite way. You can still use your NFE and then calculate the charge per se. So you don't use NFE, just use F. Yeah, just use the N times F, and then you get the quantity of charge. The mass and or volume of substance liberated during electrolysis. You can actually use the moles of electrons to calculate the moles of the substance created, and then from there you can use your periodic table to figure out the mass by using the molar mass and everything. And for volume you can use your gas constants, the volume of a gas in standard conditions or whatever conditions that you have. Like you can use PV equals to nRT or whatever you have on your hand. Yeah, just use the information to figure it out. So then the last learning outcome is the industrial process, explaining industrial processes of anodizing of aluminium and the electrolytic purification of copper. So I just mentioned the electrolytic purification of copper, which I think is pretty much the same thing. You just have the silver and all that dripping as slag at the bottom, and the zinc just staying in solution. Yeah, that's the copper one. For aluminium, as I was mentioning, if you have a solution, you can actually like anodize aluminium to look a bit different. So you make some aluminium oxides, or so not really aluminium oxide, but like you make some you make a thin oxide layer on top to prevent oxidation later on. So aluminium doesn't oxidize once a very thin layer of oxidation occurs. It's not really like iron, which just the rust just flakes off and more rust happens. Aluminium can stop with a very thin layer of oxide layer in the sense. So yeah. So sometimes they force it to happen by doing this process, and from there you can actually get a certain thickness of an oxide layer in the aluminium object in the sense. Yeah. So for the aluminium oxidation, the reactions that are involved would include the let me see. Yeah, you have the aluminium becoming Al3 plus, and whatever. Yeah, so the oxygen anion will be there as well. Yeah, so it will do that. So I mean, yeah, you'll just be involving the Al3 plus formation. And for the copper one, you'd have the copper 2 plus formation, and then at the other side you have going back to copper. That's the idea of the copper purification. Yeah, that's about it. I think we're done. If there was anything I didn't mention, I would have hopefully written it down or something. I hope you found this video useful, even though it was quite long. I just realized how long it is. If you did find it useful, you can press the like button and subscribe. And with that, I would like to say thank you and bye!